Hi, and welcome to this webinar. I'm going to be talking about AstroBEAM, a game I made in the last couple of weeks for one of our conferences. And the talk is not necessarily about the decisions I had with this game, it's more about how to think about game servers and how to develop them. So first of all, who am I? So my name is Hernan. I am a developer at Erlang Solutions, and I am mainly working on Erlang and Elixir. And the crazy thing is that I started on Erlang because I had to write a multiplayer game server. I used to be a game developer, used to work on mainly Flash games and some early mobile games for iOS and Android. And we settled on Erlang for multiplayer servers because it allowed us, among other things, to have a great number of players and saved a lot of money on the hosting of the games. So what I was working on this January is AstroBEAM. It's basically a take on asteroids, multiplayer asteroids, if you will. I had some time between late December, early January, where I could sort of work on this. And what I did was create AstroBEAM. Basically, it is a web game. It is rendered using WebGL, and the code is in JavaScript, but the game loop is in Rust, which I compile to WebAssembly, and I can execute that on the Elixir server as well as on the web page. So there are a lot of cool things about this, like including like the rendering. We could talk about that, but I don't want to focus on the specifics of this game, not even the multiplayer ones. What I want to focus on is what are the decisions that I had to make for the server for the game to feel good, to be responsive, to not have any weird behaviors or players complaining that they lost and they shouldn't have, that sort of thing. And how I made those decisions and why. So the first thing, of course, when we're talking about this and the game service in general, is what are we actually trying to do? And it is really simple. What we're trying to do is synchronize the state between multiple machines. It could be between two different players on different computers. It could be between 10 players in different computers, and it can be between any number of players and one or more servers. It really depends on many factors, including the type of game, obviously how many players we want, that sort of thing. But it's obviously not just synchronizing state, which we are all familiar with when we work on Erlang, Elixir, the BEAM in general. It is actually real-time synchronization. And real-time synchronization comes into play not just in video games. For example, ride-sharing apps, let's say Uber, you want to see where your car is. So you're checking your phone and you see the car moving and everything. That is a real-time state synchronization. The car knows where it is roughly with the GPS. It sends that information to Uber. Uber stores that information and sends it to you, the user, who sees it on their phone. So you are synchronizing the state. Ideally, if the ping allows and everything, you would see the car as the car sees itself, right? Like, again, the error should come from the GPS, not so much from the latency in the communication. Other example would be remote control of vehicles, like obviously not if you're going to remotely control like some rover in Mars with 30 minutes of latency, but any sort of drone or vehicle that you're trying to pilot from far away. Another would be those machines that they use to do surgery. You want to synchronize the state really well, because if you've seen how those work, they require the position of the scalpel or whatever to be extremely precise. So my point is, some of this real-time synchronization doesn't just apply to games. It also applies to many other things. VR and AR applications, this is sort of video game adjacent, but you can imagine collaborative working. Like if you see the presentations from Microsoft on HoloLens, where you have multiple people working and looking at the same, let's say, airplane engine and getting the same data about the different parts and I don't know, whatever people do with those AR glasses. And even the simplest collaboration tools, even if they are not VR, AR, Google Docs has live people editing. So you can conceptualize that as a real-time state synchronization where I am typing some text and you see it just the same I do. But of course, we're going to focus on video games. And the reason why it's interesting in video games, and I would argue more interesting than in any of the previous cases, including the medical one, which is crazy, is that it is even harder to do in video games. And the reason it is harder to do in video games has to do with, well, first of all, any latency sort of above 100 milliseconds is unusable. If your car in let's say, Uber is late by 100 milliseconds, it literally doesn't matter. Like, you wouldn't necessarily care. There are very, very weird cases where the car can move in 100 milliseconds more than the error of the GPS positioning. So it literally doesn't matter if the ping is, let's say, around 1 second. While on a video game, anything over 20 you can feel. You can get a good feel for anything over 20. In things like controlling robotics, like I mentioned before, even those, if people can control rovers on Mars with 30 minutes of ping, 100 milliseconds is not that big a deal. And generally, they are not being sent. That might change, may have changed recently with some uses of drones I've seen. But in general, they are not sent to do things that require like quick action. For example, different drones going to volcanoes in Iceland to measure temperature and to take samples, that sort of thing. The latency is important. It's not that important. Additionally, on video games, jitter becomes extremely noticeable. Jitter is when some messages, so when the latency varies. So if some message arrives late, it is extremely noticeable. Again, because you do get a feel for how the connection health is. This actually does happen as well in other systems. But again, in video games, it is extremely strong, how annoying it gets. Another issue, which is very funny, is players are constantly trying to find issues with your servers. So they're going to try to exploit it. What I mean by that is, let's say that some of the decisions you've made that we're going to talk later on the lag compensation, they could get an unfair advantage in some way. They're going to try. So that is basically another problem is that all your users are extremely hostile. And additionally, they are susceptible to unfairness, which, yeah, it doesn't pair very well. Like, even when you don't have people cheating, sometimes you see, sometimes the players will think that somebody's cheating because they got an unfair advantage due to the lag compensation mechanism that you used. And another weird, it doesn't particularly make it more complicated, but it is something that is not on every case of real state synchronization, is that it's two ways. Mostly when we talk about real state synchronization in the terms of a web server that we're using for, I don't know, a shopping cart, the state synchronization is the users telling the server what the state should be. In this case, it's multiple users telling each other, and they both receive and send updates. And of course, this is all in real time, and this is hard real time. Like, delays, like I said, of 20 milliseconds or less are great, but anything over that, you can feel it. So there are many different games. I'm calling it flavors here, but like basically there are many different games, and I chose here a sort of what I consider a representative sample of different types of games, and they are all extremely different. So some games, for example, use UDP to communicate, while others use TCP. Some of them are turn-based. Some of them have a lot of entities. Some are actually peer-to-peer, meaning that they are sort of serverless. The server only does like the handshake. Some games use extrapolation, while others do not. We'll see extrapolation later. But my point is, there is literally no one-size-fits-all solution to this. Every game is unique, and this depends on multiple factors. Mainly the type of game it is. Chess is going to obviously be very different from Counter-Strike, but even Counter-Strike and a game like PUBG that I showed earlier, with the size of the map, has to have different ways of handling the server. Even the vehicles, for example, if anyone ever played a vehicle level in Counter-Strike 1.6, you would know that the netcode does not work for vehicles. However, in PUBG, it is actually quite decent. And again, it really depends on the type of game. In case you're wondering, I chose none of these. By the way, for AstroBEAM, I did a custom solution that is kind of similar to the way racing games work, but with some differences. I would say somewhere between Gran Turismo and Quake. But again, this is not about what I did. It's about the things that I was considering. And what I considered was which of these games have features similar to what I'm trying to do. In the case of AstroBEAM, which is sort of an asteroids type game, the ship behaves with a lot of physics. There's a ton of acceleration. You don't move immediately. You don't like your movement has like a build-up in speed. So that actually lends itself pretty well to the same type of solution that a racing game would have. But there are differences because the ships do not collide with each other other than to explode. So I didn't need that sort of collision reaction and backtracking that Gran Turismo is forced to do, or the interpolation that it does. So I opted for something closer to, I would say, Quake. Meaning that I send all the updates with like a built-in delay. So yeah, that again, there are many choices to be made, and one of the first and most important is the choice of protocol. Like I showed before, some of the games use TCP, some other use UDP. And in case you're not very familiar with them, like a quick overview would be that TCP is based on a stream, so you have a constant flow of data, while UDP sends messages. If you are using WebSockets, they feel like that. However, the difference is that TCP, and therefore WebSockets, provide a delivery guarantee. They include mechanisms where messages are automatically redelivered, and this is before the application layer. So your OS might notice that a package is missing and re-request it, and it gets resent. Well, UDP does a best effort delivery, meaning if it doesn't arrive, it's up to you to ask for it again or ignore the problem. In TCP, for example, the packets can only be delivered once. Again, if the OS receives your packet twice, then it will just drop one of them. While in UDP, the OS does none of that for you. So you might need to keep track of this depending on the game you're working on. TCP also puts the packets in order. UDP doesn't, so they might arrive in order or not. The worst part is they actually do arrive in order, except when they don't. So you might be lulled into a false sense of security with this. In the case of TCP, however, how do they do the packets in order? If it's out of order, then the OS will wait. It puts the packages on a buffer and it waits. So you might have brand new information and your game is not receiving it because it's waiting for old information that is now useless. This is basically the way Quake 3 works. Quake 3 sends the update as a delta from the last acknowledged update. So if you lose one, you do not want to wait for it because the next update will contain the information that you're missing as well. It's sort of a diff or a history that is being sent. So TCP also provides congestion control. This avoids... This is only relatively important if you're going to send big messages. Well, UDP, I mean, if you want to do it, you can do it. There is such thing as TCP over UDP. It's not great. It's a lot of work to implement. If you really need it, you might as well use TCP. Additionally, yeah, like I said, TCP includes adds extra latency. Well, UDP doesn't, and UDP is actually as fast as it could get. There is not even a local buffer for UDP as it is in TCP, even though you can disable it in TCP. And finally, there is a security concern on this. Mainly, you cannot spoof messages in TCP. You really can't. You can do a man in the middle, but you cannot spoof messages once the connection is established. Well, in UDP, it is trivial. If you can send messages and sign them as a in the address part, you put a different computer than the one that actually sent this, and it is impossible for you to know. In TCP, since there is an ordering, it will be detected. If you want, you can implement the same thing TCP does, or even more secure, if you're gonna use STCP or whatever on UDP, but again, you have to do it yourself. So, bottom line, the difference between them is that TCP is reliable. It's also easier on the routers due to how NAT tables work. But UDP allows you to do peer-to-peer connections. This is actually related to the last point on TCP not being able to be spoofed. Peer-to-peer connections behind routers actually needs some level of spoofing to do this hole punching, as it's called. UDP is also fast and flexible, and it's nice that it's message-based. You can see, for example, in Erlang, when you open a TCP socket, you can use the packet option to simulate this, or you can do it yourself. WebSockets implemented on top of TCP add this message-based thing, but it's already there in UDP. And this is generally desired on a video game anyway. So there are reasons to choose either. Like I showed, Age of Empires uses TCP because basically they would need to, if they were to use UDP, they would need to implement literally every single thing TCP already has, minus maybe the congestion control. So it's easier to do TCP, and again, it's easier to host your own server as well on it. While a game like Modern Warfare 2, which I think is the last Call of Duty game to be peer-to-peer, has to use UDP purely to be peer-to-peer. If you're wondering, yes, my game, AstroBEAM, is actually TCP, much as I don't like it. I would have preferred UDP, but WebSockets are TCP. There is no other option to making video, web games, so it is what it is. And it's not terrible, but some of the decisions I made are influenced by this. For example, I am not going to implement a sort of diff from the previous acknowledged message on AstroBEAM, partially because I don't acknowledge messages. TCP does that automatically, so I'm not going to waste bandwidth and bytes on sending acknowledgements when those are sent automatically, and additionally because I know that every message will be delivered unless the connection is lost. Therefore, I might as well just send the inputs as they come. The next point that I want to discuss is something that I noticed a bit when I see other people trying to, maybe with less experience in video games, trying to dabble a bit, and it is using timestamps. So we're used to using timestamps when we do normal servers. We say like, oh, I don't know, I clicked buy in this millisecond. So if it's the last, if we're in contention over who gets the last, I don't know, pair of shoes at the store, you can use the timestamps to know. And this timestamp could be the one sent by the user, assuming that they don't lie, or it could be the order they arrive on, whatever RabbitMQ, Kafka queues that you are using. But this is useless for us in video games, and it is actually a huge issue when you try to use timestamps for this. So instead of timestamps, we use what we call ticks, and a tick is a discrete unit of time. How long? It's up to you, the developer, but you have to do this partially because the frame rate is variable. And what I mean by that is, if you're going to move a certain amount, a certain distance per frame, or you're going to end up with a variability in the speed. You can feel this in old games. In particular, old games didn't tend to use physics independent of the rendering, but if you're going to make it multiplayer, that is unusable. And you might think, wait a minute, I can use timestamps and do something like this, do sort of integrating the position, the velocity to get the position, and then you can get the velocity actually by integrating acceleration. This is kind of doable. However, you have, first of all, the floating point errors are going to eat you alive. This is not going to work in any way, especially because floating point tends to get really bad when you reach higher and higher speeds. Like higher numbers, so a high speed collision you will end up with completely different things. And regarding the collision, you actually cannot model complex physics interactions this way, at least not in a performant way. Physics simulations with even outside video games are actually done with ticks or time steps, they might be called, and basically a discretized amount of time. And additionally, if you were to use timestamp, milliseconds, nanoseconds, whatever you choose, it's just a very bad way of having what's called a tick rate of 1,000. A tick rate is how many ticks per second you get. So if you were to use milliseconds, you effectively have a tick rate of 1,000, and that is a crazy number. So if we're going to develop a game, one thing we need to do is decide what is the right tick rate that we are trying to get. And different games have different kind of values for this. Usually they can go as low as 20. Obviously chess, for example, it doesn't have this concept, but most games can bottom out at 20, and then 128 is sort of the maximum. I would argue it's too much, but some people like it. If you ever heard those discussions on 128 tick servers from certain communities. Also, higher doesn't necessarily mean better. It could actually introduce more problems than it solves. If the physics interactions are actually complicated, then having a high tick rate consumes too much CPU, and you're doing a lot of things that no player can actually render. So again, consider how high you want to go. Ideally, as little as you can get away with is a good idea. Another option is that you can actually have it as your frame rate if you know the hardware and you know that it's always going to work. So consoles and therefore awful video game ports tend to do this, where maybe the physics are locked at 30 or 60. You can see this in some old games where if you disable VSync, suddenly the physics are acting weird. Even in single player games, you can imagine how terrible this is in multiplayer. So you want it, in short, high enough to feel responsive, because if the number is too low, your inputs are gonna feel laggy already. Like you're introducing a latency. However, in multiplayer, this is actually desired, because the more latency you can introduce and get away with without, already with the tick rate, is latency that you don't need to introduce later when you're sending the messages. And this is very useful so that the game has the same game feel in multiplayer and single player. I'm very happy to say that AstroBEAM actually does kind of like this. It actually feels very similar. Because I introduce some lag whether you're single player or not. And finally, like I said before, you don't want to overload the CPU. Again, for my game, I ended up at 40 ticks a second. And funny enough, I wanted to use a different number, but it had to be a divisor of 1,000. And the reason is, I needed the milliseconds per tick to be a round number, because on the Elixir side, I'm using an interval. And I cannot use, for example, 33.333 as my interval, because then they will desynchronize. It will round down on the Elixir side, on the server side, and then the client, which is using like a while true effectively, so it actually can do any tick rate that I want. The client would advance a bit faster, because it would do 0.03 percent faster than the server, because it doesn't drop the periodic 3. So yeah, you cannot use 30, you cannot use 60 because they are not divide. They don't divide 1,000. 40 is great. It's 25 milliseconds per frame. It feels pretty good. And of course, you can always think outside the box. And this is, I'm not going to detail. I'm just trying to show you how you should think about go about thinking about this sort of stuff. But you can use different tick rates for different parts of the game, for example. The tick rates can also be variable. What do I mean by different tick rates? Things that are far away in a very big open world, those could have a lower tick rate. That is what games like Squad do. Additionally, you can have different tick rates for things you can see and you cannot. So things behind you wouldn't work in a shooter, but it actually does work in some racing games where the ships behind you are not behaving the same way that the ships in front of you do. And additionally, any cosmetic environmental destruction that doesn't really affect gameplay, you can run this at a different tick rate because the explosion, the grenade that blows up a window took a bit longer, but it doesn't really matter because it's just cosmetic. And from that, I'm gonna jump directly into trying to understand the game loop, which is what I think is the main problem when we're trying to develop a game. So I'm gonna conceptualize the game as a timeline, and like I said, I'm gonna divide it into ticks. And each of these ticks, it doesn't matter. In my game, it's like 25 milliseconds each, but this is irrelevant. This works the same no matter what it is. And I am not using frames, like I said, because this is how the frames would look. Sometimes they take longer, they take shorter, and it wouldn't be consistent. So let's drop the frames. Let's just think of ticks. And the way the ticks work is that you execute some game logic in like a tick. In this case, let's say tick 1. And the user is pressing a key or using a joystick, so you detect an input. This is, by the way, for a single-player game. That input gets executed on the next tick, so you execute it on tick 2. And so on. Any tick, any input on tick 2 will get executed on tick 3, and so on. However, we are making a multiplayer game, so let's put the server sort of in parallel, and I'm going to move it up. And let's say that the client and the server are communicating, and there's a latency between them. The latency will be in milliseconds, but we don't need to think about it that way. We can think about how many ticks of latency we have because we're not using timestamps, we're using ticks. Also, I personally use this. I know other people don't call it this way. I call ping twice the latency. So ping would be the return, and latency would be just one-way communication. This distinction is important because we'll see later some of the strategies we're doing introduce delays on latency or ping. So what happens when we introduce this latency? So very obviously the messages arrive late. So for example, here, something that an input that happened on tick 5 for the client arrives at tick 7 on the server, and the acknowledgement of the server having seen this arrives on tick 9 for the client. So if we were to make a game with this in mind, then we have to make some choices. And I'm going to go over some of them. These are not all of them, but some of the strategies that we have to deal with this. So the first and the most obvious is add input latency. In this case, I'm sending a message saying move on tick 9. So obviously the client and server know what the latency is. This is easy to calculate by sending some messages at the beginning, and on every other message, when you send a reply, if you send a timestamp, you can calculate it. So in this case, on tick 5, the user detects a key press and sends it to the server saying apply this on tick 9. with the expectation that by the time tick 9, the response comes from the server, tick 9 will be ready and it can be executed. Before you ask, yes, this should say tick 10, but it doesn't matter. Basically, it's, you know, whatever. Assume that instead of 2 ticks, it's 1 tick and a half. I just wanted to sort of send the arrows to the center. Another option, so this option is adding input latency, and this is why I said it's so nice that choosing a tick rate is already giving us some input latency, because if I try to do this with milliseconds, let's say a tick rate of 1,000, then I have to introduce that latency artificially, like by adding this number. Another option, I can apply the input immediately and then backtrack on the server. What I mean by that is I detect the input on tick 5 and I apply it on tick 6, just like you do it when it's a single player game. And the message, whenever it arrives to the server can go backwards and apply it on tick 6. This doesn't let you teleport too much, because you're supposed to, if you're gonna do this, you're gonna send a message every tick. So at most you can fake delay some messages, like by holding them back and then sending them in burst. But it shouldn't affect you too much. Like, it's hard to take advantage of this, but it is a nightmare to code. It has some advantages. For example, it is extremely responsive. It feels just like a single player game, because it is. It works exactly the same. But it does provide advantages if you're lagging, funny enough, which means that you can fake lag to get those advantages. This is done in some older games. I think Unreal Tournament, the old one, did something like this. And then you would see other players teleport, but I'm getting ahead of myself. And another option is to sort of do a mixture of both. Instead of saying I'm going to move in the tick that I detected plus the ping, I can do it plus the latency, right? So if I send a message on tick 5 and it takes 2 ticks, it will arrive on tick 7 to the server and client, and then they can both do it at the same time. So in this case, the message says move on tick 7 as opposed to tick 9. Obviously, not all messages will, thanks to jitter, not all messages will arrive exactly 2 ticks apart, meaning that either client or server might need to backtrack on this. But this is actually a pretty good solution, and this is not too dissimilar from what most action games tend to do. This is a pretty standard way of handling this. But we are talking about multiplayer games, and for some reason I was talking about single player games that you want to synchronize with a server, maybe as an anti-cheat measure. So let's add another player and see what happens. In this case, I'm adding another player, and this other player has 3 ticks difference with the server, just to add an extra layer of complexity. Not every player is going to have the same latency, obviously, the same ping, and the ping also varies over time. So if we look at what happens, is that we're always going to have to backtrack. No matter what the previous cases were, we're going to have to backtrack. In this case, I am doing the last method, where I am sending the message to move in the current tick plus the how many ticks of latency you have. So I'm saying on tick 5, I say I need to move on tick 7. The server does this, and so does the client 1. But then client 2 is going to receive this message late, 3 ticks late to be precise. So now it needs to backtrack. And you can imagine that if you have more than 2 players in this, client 2 will need to, assuming that they are the highest ping, they will need to backtrack on every single tick of the server. This is horrible. And the same actually happens for any message actually sent by the slower client. So it's not even just a problem for the lagging players, which you could deal with. Actually, everybody is going to suffer like this. In this case, client 1 is on tick 10 when it finds out what actually happened on tick 8. So it will execute tick 10. It will jump backtrack to tick 8 and then go and do execute 8, 9, and 10. So since it already had executed 10 or 9 before, now it sees like that the path changed. So if he was shooting at someone, now that person is somewhere else and it didn't get shot. This is extremely annoying, and it's one of the biggest complaints people have on multiplayer shooters. Okay, there is an easy solution to this, the obvious solution, which is you delay all inputs by the maximum ping, not latency, but ping of all the players. This works, and in fact, Age of Empires 2 does this. To my knowledge, Age of Empires 4 doesn't, but Age of Empires 2 does. And even in the case of Age of Empires, the game even pauses. So if the message arrives too late, so let's say in 5 ticks or something, like after the expected one, then the game actually pauses for every player until until everybody receives this message. This has to be done because there are so many units to synchronize that it's better to pause the simulation than trying to backtrack it. Also, backtracking wouldn't work. This also means that a lagging player makes it terrible for everybody. And you can also notice this: if somebody disconnects, the game actually stops, sort of pauses. And then the other players need to vote whether they keep waiting or disconnect, because nobody can connect mid-game, because again, it would be terribly difficult to synchronize the status of everybody. This is obviously not the only solution. There is another one that is very common. This is sort of done by Quake 3 Arena. The players see an updated version of the game. Now, I tried so much to make a graph that works for this, like to show it to you, but it's very difficult. Basically, what happens in this system is on tick 5, let's say, client 1 moves. This gets applied immediately on tick 6, like we talked about before. It's similar to option 3 in that sense, and it sends a message to the server. The server, every tick, it sends to every player, and here I'm only highlighting the ticks where some input happened. It sends to every player the current state. So then what happens is that the players will always know an old version of the server. There is no prediction, there is no extrapolation, there is no interpolation. There is some interpolation actually, but like not related to this. That is basically to interpolate between frames. So when the tick rate is higher, smaller than the frame rate. What happens in this case is that the position of everything is like you're seeing them on the past. So if you want to shoot at someone, you don't shoot them where they are like you do in Counter-Strike. You shoot them where they are going to be. And this is why Quake, if you ever played it, has that sort of metallic ping when you hit an enemy. That's because you can get a feel for how ahead you have to be of the player to hit him with, let's say, the machine gun, by moving like, some number of pixels to in the direction it's moving and shooting there until you hear the pings. This sounds terrible, but it is surprisingly good, and your brain does the lag compensation on its own. It's not too dissimilar from shooting enemies in Space Invaders, actually. Also, Call of Duty, when you shoot at someone and the X appear on your crosshair, exactly the same thing. And of course, you can, again, I'm reusing the slide. You can think outside the box again if you want. There are so many ways to tackle this, and different genres will have different tricks that are possible. For example, the tricks that work on Quake will not work on a racing game. You cannot have an old state. You cannot see an old state, because then are you going to crash against a ghost? Everybody's going to see a different crash. So a racing game probably cannot even consider doing this. Well, it works perfectly good for Quake, but it feels very unrealistic on a game like Counter-Strike, where it's so precision-based. In that case, if you do this sort of thing and you need to know how to shoot in the air, when people tend not to move while shooting because of reasons, again, you need to think about how to tackle the problems that you have. There is a lot of playtesting involved, and there is a lot of Googling about how games similar to the one you're developing actually solve these issues. And what are the trade-offs? Because every single solution has a trade-off other than playing multiplayer in split screen. That is the one that has no trade-offs. Other than the physical location of the players. What I did for AstroBEAM, sort of an example of what I call the option 3, where I just increase by the latency of the worst player. And since this was for a conference, I know that the ping is going to be roughly the same for everybody, because even though you can play it from anywhere, you are going to be playing it mostly from the same room, meaning the same ping to the server. So I can get away with doing the backtracking on the slower client. So for example, when it's going to be running now in a couple days in AstroBEAM Americas, and if you had the IP of the server, you could join and play with them, but you're probably going to get a higher ping if you're doing it like I am doing, joining from Europe. So yes, some examples on things that you can do for this is you can interpolate between the current position and the server position. This is what racing games tend to do. So they extrapolate what the server would be seeing right now, and then they interpolate with the position that they pre-calculated before. This is why sometimes in a racing game you can see a car moving in a physically impossible way. So like moving side to side. The car actually moved properly on their local machine, and you get their position sort of delayed, and when it interpolates between them, it interpolates in a way that is physically impossible, including things like teleporting through another car if the lag is high enough. Another option, you can mask input lag with acceleration and animations. Racing games, again, obviously, but Age of Empires does this. When you select units and you tell them to move, you can see them all rotate in place before they start walking. And this rotating in place is actually time for the message to get to the other players. When it arrives, they actually might rotate in place slightly faster. This is barely noticeable, but it makes it so that it feels the same when you are playing locally. Again, the maximum the maximum latency that this can tolerate is decided by these animations that are sort of pre-built in many cases. So again, be careful with that. But yeah, CSGO does the same thing, actually. Masking input lag with acceleration. This is why most games actually you don't accelerate instantly, even if it would feel nice in many cases. You can use animations to hide the backtracking. Street Fighter is a decent example of this. There is an entire talk on the GDC about this. You can find the video on YouTube. If you're interested specifically in fighting games, and you are also going to use UDP. If you're going to do it with a server, you probably are going to need a different solution, but they do it peer-to-peer with UDP. It's perfectly explained. There's also extrapolation. Like I said, this is what I was doing a bit on AstroBEAM, because the movement of the asteroid is so predictable and there is no input unless they explode. It's not the most common though, because it forces you probably to interpolate later. It can do weird stuff. It can feel weird. It's normally done in racing games, which is why I thought it would apply to AstroBEAM. And after trying the game, yeah, it feels good to do it. Other things are like the audio cues, like I mentioned on Quake 3, the ping when you hit. And yeah, there's so many more. And they include things like who to favor if there is a problem. So for example, Counter-Strike favors the person shooting, not the person getting shot. So if there's a discussion of whether you were seen or not, so on your computer you were hiding because you were already, you ran past where you could be seen and you're hiding behind the box, but the other player didn't see that, so he thought he saw you. Actually, the game benefits the shooter, not the getting shot in CSGO. You can also see if you try to penalize high latency or try to mask it a bit, which again goes back to what I mentioned earlier on maybe even in those cases faking high latency can almost be a way to cheat or get an unfair advantage. And so many more. There is so much that I could talk about here, like the fake bullet CSGO has. And I just want to close it with I think the best quote by John Carmack, when he was talking about how upset he was about the client-side prediction and having the delay for the on the local movement in Quake world in 1996, 97. He wrote on Usenet that, yeah, he doesn't like it, but this is the only way it works, and I am pragmatic above all else. And this is what you should do as well. When you're gonna sit down, and if you're gonna sit down and develop a game, a multiplayer game at that, think about this. You're pragmatic above everything else. If it feels good to play, it doesn't matter if it's physically correct. It doesn't matter if it's accurate. It doesn't matter if it's optimal. What matters is, does it feel good? And the feedback I got from AstroBEAM in the conference was that it does feel good. So clearly I made the right decisions. Could there have my better ones? Definitely. But it feels good, and that's all that matters. So thank you. And yeah, if you want to contact me, you can. You can probably get my email somewhere here at ESL. I don't know, LinkedIn. You can find me. I'm on GitHub as well. So yeah, thank you very much.